Hi, my name is Peter Røen, and in this video I'll just shortly show you how to operate my server for checking if there are steric or topological obstructions or hindrance for aligning a protein model to the correct 3D structure of that protein. You will find it at this homepage. So there are two versions, the one that's most stable and the intended one with more functionality. We'll stick to the stable one here. You need to upload PDB files. They can have any last name you like. So I'll just take one here. It's from the last, it's on CASP 14 prediction competition, and here I have to upload models, and I can just take a bunch of models. Also here it's models of another protein that's included in my set. It takes a little while to actually read them, the PDB files, and now they are read. The first thing I can do, I can compare the target to all the models and get output in this list. You would see there's no comparison going on to the completely different protein here, and the reason for that is that we are right now assuming wanting to find an exact sequence match between the target and from the target as a subset of the model, and that's of course not possible if it's a completely different protein. But you could instead just take a geometric alignment, global RMSD alignment, and then you can do a comparison. But of course not a sequence comparison is possible in this situation. So here you can sort the lists after each column if you like to search for something. The most interesting case is this model 15.5. I can take it from my list here and generate some figures. Takes a little while. And here it shows up. In this plot you see that there's steric clashing going on when doing the interpolation from the one structure to the other structure, from the model to the target. And all the black spots here are places where the distance between amino acids gets too short during the linear interpolation between the two structures. In some other places the backbone actually passes through itself when going from the one structure to the other one. Some of them the program can see that it can avoid them if it's allowed to change the morph inside the configuration space, and right now it's told that it's allowed to rearrange 15 amino acids of length, trying to avoid the self-intersections that happened before. So these 3 self-intersections can be avoided that way, and this last one cannot. But since it involves residue a little bit less than 15 in number and a little bit more than 100 in number, then you need to rearrange a good third of the protein, and actually it is capable of doing that. If I say you're allowed to rearrange 45 amino acids, then it actually finds a detour in the configuration space through self-avoiding configurations between the two structures. It's a little bit difficult in this plot to see what it is that's going on. So applying smoothing of the backbone typically helps. I'll set this number down again. I'll just redo the calculation here. After the smoothing, it's hopefully easier to get an idea of what's going on, and you can sort of see it from this direction. You have a part of the target, the yellow curve here in front, the other part is behind. That's how it is in nature. That's target structure. But in the model, this blue curve actually enters through that blue loop. So instead of having in the correct structure the two loops are away from each other, then in the model the one loop is passing through the other loop. So it's basically interlinking like that. So this is what the program searches for, that self-intersections occur when you do the interpolation from the one structure to the other one. It checks if you can avoid those self-intersections by rearranging at most the number of residues you enter here. It deletes as the maximum number of these self-intersections and actually does it in a way that where the detour is as short as possible. So this gives you an idea if your models are threaded in the same way or differently from the target you have. We can switch to just having MSD based superposition, and I can do that for showing sort of the last functionality here. If I can do all against all search, and I don't want that many model structures in the list, so I'll just take a shorter list. These are actually all the models from one of the predictors in the CASP 14. So here are the models, and I now do all against all search. And what you see is that between most of the models there are self-intersections, and several of them are what we call essential. So they would have realized, they had access to this program, that this part there's a difference between the models, and then started perhaps asking themselves, how should the threading actually be in the models? You can of course also submit a set of homologous protein structures that you are using in your model prediction. Lastly, the PDB reader I'm using here is only taking the first chain of the PDB file, and it's taking the first model in the PDB file if there are more than one. So if you want to use chain 2, you need to make a PDB file where chain 2 is the first chain in that PDB file. There's a longer version of this video where I explain more about how the algorithm actually works, but this is just to get you started using the server. Hope you will enjoy.